Alright, hey everyone, welcome to the next installment of Chem 390, where in this lecture we're going to talk about the effects that wildfires have on the troposphere. So last lecture was all focused on the stratosphere. This time we're going to move a little bit closer to Earth and we're going to focus on the troposphere. And specifically we're going to talk about some of the forms of particulate matter produced by wildfires that we haven't covered yet, or at least that we haven't talked about in detail yet. So I'm talking about like elemental carbon, the NOx, the organic carbon. We talked a little bit about organic carbon last time because it was sort of the liquid that allowed chloronitrate and hydrogen chloride to dissolve into to ultimately deplete ozone in the stratosphere. This time we're going to talk about it from a different perspective. What else can it do? And I don't think we're going to be covering any other forms of particulate matter in this lecture, so let's, before we get into it, do a quick recap of last time. So last time was all about ozone destruction, specifically stratospheric ozone destruction. Running out of room. Stratospheric ozone destruction, where we learned that wildfires produce a bunch of organic carbon. So let's draw some flames here. I'm not a very good artist, but here, this is going to produce a lot of organic carbon, which in a pyrocumulonimbus cloud will have a significant amount of upward draft, driving this into the upper regions of the stratosphere, where the organic carbon, remember, is a particulate matter, and it's actually in the liquid phase, so you can think of these organic carbons as little teeny tiny liquid droplets way up in the stratosphere. What can happen here then is that the hydrogen chloride and chloronitrate that already exist in the stratosphere simply because chlorofluorocarbons take a very, very long time to completely degrade in the stratosphere. So there's still plenty of residual hydrogen chloride and chloronitrate, and in addition, we also talked about how wildfires, in some cases, can produce chlorine on their own. The source isn't really super well defined. Pesticides is certainly a big one, where pesticide chemicals tend to use a lot of chlorine. But anyway, this chlorine emitted by wildfires or the chlorine produced from chlorofluorocarbons form hydrogen chloride, chloronitrate. These can dissolve into the organic carbon. Hydrogen chloride is significantly more soluble in organic carbon than it is in water, like with polar stratospheric clouds with the other ozone hole. So this is something that can increase the amount of ozone depletion. But anyway, they get converted to Cl2 in the organic carbon liquid phase, and then eventually that Cl2 is liberated, absorbs UVC light, and forms a bunch of chlorine atoms, which then deplete ozone. Okay, and this is obviously not a good thing because ozone in the stratosphere is good for removing or protecting us from harmful UVB radiation. So because of this ozone depletion caused by wildfires, we can expect in the coming future, as wildfires increase in severity and frequency, that the amount of UVB reaching Earth's surface is higher, so likely an increase in skin cancers and cataracts, for instance, and other harmful health effects are predicted based off of this science. Okay, and then, like I said, today we're going to be focusing on the troposphere. So let's do the first two, elemental carbon and like cloud formation from particulate matter. because this is going to be very minor in terms of what we're going to focus on in the lecture. We're mostly going to talk about, again, more ozone in the troposphere, believe it or not. So let's quickly just knock out elemental carbon and the effects that just wildfire particulates have in general on the troposphere. So elemental carbon, I have a picture here of a big semi-truck with these big smokestacks coming out. Well, this is elemental carbon. Something naturally produced by these large trucks where it's simply just unburned fuel or fuel that isn't burned efficiently. So in your car, we have hydrocarbons. I'm just using octane here as an example. Your fuel is given an octane rating that's really more a measure of how closely and efficiently it burns to a specific isomer of octane. So not super important, but all I'm trying to say is that fuel, let's just pretend all the fuel in your car, all the petroleum is octane. So this is going to react with O2, and it's going to form CO2 and water. I'm going to try to balance this on the fly here. Not really an important detail. Okay, this is a little bit tricky, but I just don't want to put fractions in here. Okay, it's going to form basically carbon dioxide and water if it were to burn perfectly. In reality, it doesn't burn perfectly, and some elemental carbon and organic carbon is formed on the way as this octane, this fuel, is converted into CO2 and water. So this stuff is emitted by cars. And elemental carbon particularly is emitted by diesel burning trucks for reasons that we don't need to get into, okay? So this elemental carbon, as you can see from these pictures, so I have on the bottom here a wildfire or perhaps a residential fire. It's hard to tell what image I got here, but it's a fire, and the smoke is very black, okay? So elemental carbon can be characterized as, it's often sometimes called black carbon, where it's basically just these little particles, sometimes big particles, but let's just assume that we're talking about particulate matter in the atmosphere here. So these are little particles of just black carbon, okay? And what these can do is these can absorb sunlight. So the sun gives off, we talked about in our last lecture, really all wavelengths of light. What's important in this case is the visible light, that this, since the carbon is black, that's an indicator that it's absorbing every single wavelength of visible light. If it was white, like mist or fog, or even clouds, that means it's reflecting all of the light. So just fun fact for you. So the elemental carbon absorbs visible light, and it retransmits it into the atmosphere as heat. So these squiggly arrows, well, I guess I drew squigglies for visible light, but I'll just label it. This is heat, which really is just the motion of atoms. So really what this carbon is doing is it's absorbing visible light, increasing its temperature by translating that light energy into mechanical motion or movement to increase its temperature, and it's spreading this motion to nearby molecules, nearby surrounding air mass, and increasing temperature that way. So the net result that elemental carbon has in the troposphere is that this generates a local heating effect, because of the elemental carbon absorbing visible light, converting it to heat, increasing temperature in the vicinity in which the elemental carbon resides, okay? But that doesn't necessarily mean that wildfire smoke causes just the area surrounding it to heat up because there's a compounding factor at play where um, the particulate matter in wildfires can also lead to cloud formation. I had an image in the previous lecture when I was talking about pyrocumulonimbus clouds. It showed like clouds and precipitation resulting from wildfire smoke. And the reason here is that particulate matter can act as we'll call it a seed particle. That's one way to call it. For H2O to, we'll say, crystallize on. I'll explain what I mean by this definition in a second. I realize there's kind of a lot of jargon in it. And this ultimately leads to clouds, because that's what clouds are, right? It's like suspended water in the air. And what I mean by the acts as a seed particle for water to crystallize on is that in order for a solid particle of water to form, for water to freeze, essentially, it usually needs some sort of like seed crystal or something upon which the water molecules can start to bind and build up as an extended solid. You may have seen this with like some super cooled water that where people can you can like take a water in a water bottle, and as long as the insides of the water bottle are very smooth and relatively defect free, the water will cool down well below the freezing point, and you can like smack it, and then you'll watch the water sort of crystallize and propagate throughout. So that the reason why water doesn't necessarily freeze, even though it is at a freezing temperature, is because the water needs to physically start to form ice and crystallize upon something. So if there's no like rough scratches in this example, the water bottle, then the water won't crystallize. It'll just get really, really cold. And the act of you smacking the water bottle essentially can introduce a scratch for the water to bind upon, or it can provide enough kinetic energy for the water to overcome the energy barrier of forming a crystal and propagating the structure of ice throughout. So similar phenomenon here with wildfire smoke and clouds, where as you can see in this little image I have here, there's a lot of particulates in wildfire smoke. So these particulates, I'll just draw it again as like these little dots, can allow water molecules to essentially bind to them and start to crystallize around them, something that's called a seed crystal or a seed particle, and this ultimately will result in cloud formation. And clouds are really interesting in terms of temperature effects because they are there's a lot of factors that determine the temperature effect clouds can have. The general consensus in the scientific community is that clouds generally create a local cooling effect. So this actually creates a local cooling effect because light from the sun hits the clouds and then can reflect off back into space, not ever reaching Earth's surface. So this sort of is an interesting interplay where there's no just like one ubiquitous, consistent net result to temperature from wildfire smoke. It can generate more heating from the elemental carbon absorbing visible light and retransmitting that out as heat, or it could generate a local cooling effect, like by forming cloud formations. And an interesting example of this was in the 1990s in the Philippines, Mount Pinatubo erupted. Pinatubo erupted in the Philippines. And what was observed was a lot of cloud formation because a lot of particulate matter, mostly sulfates, I believe, but still particulate matter sort of surrounded the area and caused a lot of clouds to form. So this resulted in local cooling due to cloud formation. I realize I should have given myself more room on this slide or just started a new one, but this is the last thing I'm going to write on here. But there was a local cooling effect that resulted from this volcanic eruption because all the particulate matter that was released into the air acted as seed particles for clouds to form, ultimately just really covering the area in cloud cover that reflected light back into space, ultimately resulting in a net cooling effect. So yeah, these are two sort of effects that the compounding effects that, or sorry, like contrasting effects that the particulate matter in wildfires can result in. They can result in cloud formation, local cooling, and also local heating due to the soot and elemental carbon absorbing visible light and retransmitting it as heat. Okay, so now let's get into the main topic of today's lecture, and that's ozone again. So like I said last time in our last lecture, ozone exists everywhere in the atmosphere, so in the troposphere and the stratosphere. It is very good in the stratosphere because it protects us from UV light. It is very bad in the troposphere because ozone, this molecule O3, is very, what we call in chemistry, oxidizing. We don't need to know the significance of what it means to oxidize something. I'll just give you an example that you're probably aware of. So you might be aware of bleach. I should say like bleach. So bleach, sodium hypochlorite. I guess we can include that just because it's interesting. So sodium Na hypochlorite OCl. So bleach obviously is very toxic to ingest. Ozone acts in a similar way, has a similar reactivity. It's very oxidizing. So if you breathe it in, it will oxidize your mucous membranes in your like lungs and stuff, and resulting in really, really, really negative health effects. Not good. So you do not want ozone in the troposphere. You would rather have it in the stratosphere where you're not breathing in stratospheric air, so you're not breathing in that ozone. Okay. So ozone in the troposphere is typically formed through a phenomenon called photochemical smog. And this phenomenon generally occurs in regions that have low wind speeds and higher temperatures and lots of cars. So big metropolitan areas are perfect candidates really for photochemical smog to form. So like LA, New York, Tokyo, Paris, Mexico City, there's like pretty much any major city around the world will have problems with photochemical smog. And the reason for that is because this generally forms from automobile exhaust. So automobile exhaust, I mean, we kind of talked about with the truck example here, is going to form a lot of organic carbon because no matter how perfect your fuel is in terms of octane rating, it's not going to burn perfectly to CO2. Like for every molecule of fuel that you burn, you're not going to convert all of that to CO2 perfectly. There's going to be intermediates that form along the way, some organic carbon that forms along the way. So automobile exhaust includes organic carbon from incomplete burning. Okay? That says burning, not bumming. It looks like booming or something. Burning. And then also a lot of NOx emissions, NOx. And NOx generally refers to NO or NO2 that can form. And NOx forms not from fuel in your car. You generally don't have a lot of nitrogen content in petroleum, but NOx generally comes from, that's supposed to be an arrow, generally comes from the fact that if you mix O2 and N2, which we learned last lecture, that's about 99% of our atmosphere composition is oxygen and nitrogen. If you mix this in the presence of, let's say, a very, very hot engine, this can form two molecules of NO and ultimately result in NOx emissions, okay? So the general chemical reactions that organic carbons and NOx do to form photochemical smog are admittedly very complicated. I'm going to give you a very distilled version. So the first important thing to note is that Earth's atmosphere is oxidizing. So there's that word again. I guess I'll try to give it a good definition here. So what I mean when I say the Earth's atmosphere is oxidizing, think oxygen atoms, okay? So if what oxidizing means, or what it can mean, is that if you were to just release a chemical, a molecule into Earth's atmosphere, over time, oxygens will be added to it, okay? So take, for example, if I have a molecule of methane, CH4, in the atmosphere, what will happen is it slowly but surely, over the course of, I want to say close to a decade, don't quote me on that, I'm not confident in that number, but over a pretty decent time period, the methane is slowly converted into first formaldehyde. You don't need to know the names of these, it's just whatever. Don't worry too much about the names. So methane gets converted to formaldehyde, which can get converted to carbon monoxide, ultimately getting converted to carbon dioxide. So over time, this carbon gets oxidized, so it slowly gets more and more oxidized, i.e., oxygens are added to the carbon, okay? And you could argue for the hydrogen, because there's also hydrogen in this. The ultimate fate of this is to become water, H2O, so again, oxygen being added to it, okay? And the main chemical responsible for this oxidation process in the atmosphere is the what's called the hydroxyl radical. So OH, and when I say radical, this is just a term for a class of chemicals where this oxygen atom has an electron that I'll signify with a dot there that is unpaired. Typically in the real world, atoms want to pair their electrons up for reasons related to quantum mechanics that we can't really get into. But basically, if things have an unpaired electron, they are very, very, very reactive, okay? So this hydroxyl radical naturally exists in the troposphere. We don't need to talk about its sources. It's basically loosely related to water vapor in the atmosphere is how it's formed. But this hydroxyl radical is the thing that will react with molecules and oxidize them, or at least it will start their oxidation process. So something like methane, for instance, CH4. If you release methane into the atmosphere, it slowly reacts with hydroxyl radical, which ultimately converts it all the way to CO2, which, by the way, CO2 is the most oxidized form of carbon and is a very stable molecule. So really what the Earth's atmosphere is doing is taking this molecule of methane, converting it to a more stable form, okay? And the reason this is, I mean, we're getting to photochemical smog, just bear with me here. So what this hydroxyl radical does, OH, is it will react with organic carbon, ultimately forming through a series of reactions that, like I said, we just don't have time to really get into. They're also just not that important. This will also ultimately form what's called a peroxy. So per just means like extra in chemistry. So it's like a hydroxyl radical with an extra oxygen. So peroxy, extra oxygen. And this is called a peroxy radical. So again, something with an unpaired electron, still very reactive, but it forms this peroxy radical, which is a very important component, precursor of photochemical smog. And it ultimately takes that organic carbon, which, remember, organic carbon is just like some proportion of carbons, hydrogens, and oxygens usually. I'll say CXHYOZ. So it's some form of carbon, like let's say formaldehyde here. Formaldehyde's a great example of an organic carbon, where it's carbon that is somewhat oxidized, but not all the way to CO2, okay? So this hydroxyl radical will take that partially oxidized carbon, convert it all the way to CO2, and also form peroxy radicals as a result, okay? And this peroxy radical is very important because it reacts with NOx to ultimately form ozone, which is a major component and major indicator of photochemical smog. And the reaction for that is NOx. So let's say, you know, the nitrogen oxide, the NO, that's technically nitrous oxide, but whatever. The NO molecules that form from, let's say, O2 and N2 mixing near a very hot surface. If this were to react with peroxy radicals, so OOH, I drew those O's really far apart. I'm not really sure why I did that. OOH, this can form NO2, which NO2 can absorb UVA light. So remember, in the troposphere, there's plenty of UVA. There's really no major chemical or molecule in the stratosphere that is absorbing that. So in the troposphere, plenty of UVA. NO2 can absorb some of it, forming, again, NO plus an oxygen atom. So this is similar chemistry to the stratosphere because now this oxygen atom can react with O2 and form ozone, like so, okay? So this is a lot, I understand. There's a lot going on here. And here, let me just, because I think my camera might be blocking this. I should just turn off my camera. I really don't even need it on. Let's draw this up here. So this forms NO plus O. The oxygen atom specifically can react with O2, ultimately forming O3, okay? So in order for photochemical smog to form, you need both organic carbon and NOx, NOx. You need sunlight because the NOx needs to absorb UVA to form those oxygen atoms. And you also need oxygen, so air. I mean, oxygen's everywhere. That's kind of a given. But you need the oxygen as well, okay? And then let's go ahead and write an overall reaction for this stuff. For these smaller reactions, what's important for you to know is that organic carbon forms these peroxy radicals as it is oxidized to CO2. The peroxy radicals react with NO to form NO2, which can absorb UVA, which forms free oxygen atoms, which can react with oxygen molecules and form ozone. Okay, so an overall reaction for this process would look something like this. So we needed NOx, we needed organic carbon, we need light, we need UVA light, and we need O2. And through those reactions that I showed you on the previous slide, what these do, my arrow is like going downwards almost. What these do is they form ozone. And technically, one thing I didn't tell you is that NO2, if there is no light present, NO2 can react with hydroxyl radical, which is in abundance. Well, not in abundance in the atmosphere, but it's going to be present regardless of NOx emissions or organic carbon emissions. NO2 can react with that and form what's called nitric acid, HNO3, a very, very harmful chemical to breathe in. So that is an additional product here. And this is sort of just the overall reaction for photochemical smog. So really, the molecules that are really harmful in smog are ozone and nitric acid. What was I going to say here? Oh yeah, harmful. These are not good. And like I said, this is going to be sort of in a region, like smog is going to be more prevalent in a region. Mostly the thing that is limiting here is NOx and organic carbon emissions. So this is going to be very prevalent in regions where there's lots of cars that are producing this stuff. Luckily, today, smog isn't as big of an issue. It certainly still is, but it's not as big of an issue because this is what your catalytic converter in your car removes. So your catalytic converter let's say removes these from exhaust. So basically what your catalytic converter is a slab of expensive metal. So like rhodium could be used or platinum could be used, precious metals, which is why they are often the target of theft. People want to steal catalytic converters because the metals inside of them are very valuable. But what those catalytic converters do is they take the NOx, they convert it back into N2 and O2. So I guess let's be more specific so we have a balanced equation here. So they take those NO molecules, they basically just do the reverse reaction of what I have here. They just go backwards so that NOx emissions are lower. And you know, it's not perfect, your car will still emit some NOx, but your catalytic converter significantly reduces the amount of NOx emitted. And then the organic carbon is fully oxidized to CO2. So this is what your catalytic converter does so that the NOx emissions and organic carbon emissions are lower, ultimately resulting in less smog formation. Okay. All right. So, so this is sort of like what smog looks like. This is Los Angeles, for example. So smog is very characteristic or characterized by this just thick, brown, yucky looking layer over cities where the brown color actually comes from the fact that NO2 is brown. So remember that one of those major intermediates along the way of smog formation, NO2, this thing is a brown chemical. And that's why smog has that sort of characteristic brown, yucky color. But really, what's in here also is some ozone. During the day, remember, ozone formation is going to be dependent on the presence of UVA light. So during the day, lots of ozone. During the night, lots of nitric acid, because the NO2 is no longer being split by absorbing sunlight. But in general, really just not good stuff to inhale. And in fact, I worked in LA for a couple years, and one of my more senior colleagues told me about when he first moved to LA in the 1980s, and he said the smog was so bad that you would go outside for like a jog, and you'd have to stop after like 10 minutes or so because your lungs were just literally burning, being oxidized by all of the ozone in the air. So really, really not good stuff to inhale. Luckily, the World Health Organization has much stricter regulations on how much ozone is allowed to be in the air. So I guess we can touch on that because it will come up later. So the World Health Organization regulates the amount of, or I guess provided guidelines, recommendations for maximum permissible levels of ozone in the air. So ozone is the major molecule that is monitored when to quantify the amount of photochemical smog. So ozone is really the important chemical here. So ozone levels need to be less than so I'm going to give weird units here. I'll explain what they mean in a sec, but like 60 to 70 parts per billion. So parts per billion, or ppb, just means that if you were to measure, make a measurement for every 1 billion gas molecules in the air, 60 to 70 of them at most can be ozone, okay? And I think at the height of like LA's smog problem, ozone was like in the range of like 380 parts per billion, which is like insanely high. And just to provide some comparison here, in the stratosphere, so let's say up here, the stratosphere is going to be a little bit higher than this likely, but this is as much as I got in this image. So in the stratosphere, ozone levels are about 15 parts per billion. So in the stratosphere, where it is good, where it is beneficial, ozone is about 15 parts per billion. Ideally, it would be 0 parts per billion on Earth's surface, but because of cars and pollution and all that stuff, it's at most 60 to 70 parts per billion. On any given day, at least in LA, from what the numbers I looked at, so in LA, you're looking at about like 50 parts per billion at most. So well below, well, not well below, but below the maximum permissible limit set by the World Health Organization. But just something interesting to think about, I think. And what we'll see with wildfires coming up is that wildfires can actually pretty significantly increase the amount of ozone in the air and contribute to a lot of bad air quality over very, very large distances as well. Okay, so hopefully we have a somewhat decent idea of what photochemical smog is, how it forms ozone, and just to reiterate, ozone is not good to breathe in. It's basically akin to bleach in terms of its chemical reactivity. Certainly, drinking a bottle of bleach is going to be way more exposure than you would get breathing poor air quality. But, over the course of decades, you can develop some really bad chronic health effects like lung cancers and other issues due to breathing in a bunch of ozone, okay? So let's look at ozone and wildfire emissions, which we actually have some recent events to look back upon to sort of demonstrate some of the effects wildfires can have. Where I forgot to put the date on here, but this map is from June 5th of 2023, where, as you, I'm sure, are well aware of, significant portions of Canada were experiencing wildfires, where what we can see here is that red is out of control. A lot of these circles are red. So there was a lot of just uncontrolled wildfires ranging up to sizes of, greater than 1,000 hectares in size. And all of these wildfires are producing a bunch of organic carbon, a bunch of NOx, and that these particulates are being carried to nearby areas through wind and ruining essentially the air quality over, in this case, and for these Canadian fires, over a lot of the US, the air quality has been really, really poor this summer as a result. So I have some figures here. So these were circulating in the on the internet back when these fires were very out of control. I guess good news is, update is that a lot of these circles are blue and yellow now, so a lot of these wildfires are contained and controlled. But at this time they weren't, and the air quality, let's say in LA, so this was Times Square at the time, was really, really poor. So this really brown, yucky looking smog over New York, well, that's our NO2, that brown, disgusting molecule. And NO2 is a precursor to ozone and nitric acid. So very, very bad things to breathe in. And I thought this picture was very ominous. It's like a video game ad that says "Welcome to Hell" with just like this really hellish landscape behind it. It's truly morbid stuff. So what we're going to talk about today is how do wildfires produce ozone? How much do they produce? How does the geography of where the wildfire is contribute to ozone production? What time scales? And then also what distances can be affected by this? So kind of a lot. I'll try to speed through because we've talked about a lot of the chemistry already that I wanted. We hit these chemical reactions. So the chemistry is mostly done, and we're just going to look at some more cause and effect relationships and not so much delve into the chemistry, mostly because the chemistry can be very, 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 very complex. Okay, so let's start with just ozone formation by wildfire emissions. How does ozone form by wildfire emissions? Well, we kind of already talked about it. So wildfires produce a lot of organic carbon and a lot of NOx. That was one thing that we touched on in our first lecture of the course. These two being very important precursors to smog. And I need to correct something I said in the first lecture. So in the first lecture, I said, in first lecture, just the one, I said that NOx can be formed in wildfires from the reaction of, N2 plus O2 in the presence of heat will form 2NO. And I was thinking of like NOx emissions from internal combustion engines in cars, but this is not true for wildfires. So this is not true for wildfires. So I apologize for the incorrect information there, but the NOx emissions from wildfires, so NOx from wildfires is largely dependent on the nitrogen content in the plant matter that is burning. Okay? So that's really, really, really important for thinking about ozone formation from wildfire emissions, is that the amount of NOx that will form is going to depend on the nitrogen content in the plants, where plants, like I said, can be composed of carbohydrates. This is what they are mostly composed of. So plants are mostly this, but you may know that nitrogen in the form of like fertilizers is very important for crop growth and plant growth, because plants also need to form proteins. So plants also need to form proteins. And the way they do this is by fixating nitrogen in the soil. And when I say proteins, like one example would be something like, because proteins are chains of amino acids, so much like carbohydrates can be chains of glucose molecules. So an example of an amino acid, the most simple one is something like glycine. So glycine has the chemical formula of C3. Okay, sorry, I had to draw it out because I have the structure in my mind, but not the formula. It's more common to think of structures in chemistry, not so much formulas. But anyway, so it's C2H5NO2. So this is really a characteristic element in proteins is nitrogen. Okay, so since plants are living beings and carry out their biochemical process with enzymes, with proteins, they have naturally some nitrogen content in them, okay? So when we're talking about NOx emissions from wildfires, it's really how much nitrogen is in the plants, or like relative protein content. And we don't need to get into very specifics of like what plants have, like, you know, what percentage of nitrogen versus others. We can just focus on like regions and geography, and how the like relative geography will dictate nitrogen content in the plants. Okay, so this is really the main distinction between ozone formation from wildfire emissions versus ozone formation from automobile emissions, is that the emissions of NOx from wildfires depends on the fuel, whereas emissions of NOx in automobiles is simply because there's nitrogen and oxygen in the air at all times, okay? But other than this, the process is exactly the same. The organic carbon reacts with the NOx, reacts with light, and with O2, and forms ozone and HNO3. Okay, so the process is basically the same chemistry, same everything. There's just some slight differences here. So let's talk about geography dependence of ozone production from wildfires. Okay, so like I said, nitrogen content in plants isn't going to be the same for every plant. It's going to vary. So in general, tropical regions, I should say plants in tropical regions, tend to have more nitrogen content. The actual chemical reason for that isn't very clear to me. All I know is that in terms of an ecological perspective, the plants in the tropics, for whatever reason, have evolved to be better at absorbing nitrogen from soil. So for that reason, they have more nitrogen content in tropical regions. So when I say tropical, I'm talking about like near the equator. So think like, you know, Northern Africa, Central America, those sorts of places. So plants in the tropical regions have more nitrogen and therefore more NOx emissions. Okay, and inversely, plants in like boreal or temperate regions, so plants in boreal or temperate regions tend to have less nitrogen, and this results, you guessed it, with less NOx emissions. Okay, so this actually results in some really, really interesting differences in ozone productions based on if the wildfire is in the tropics or in like temperate boreal regions. So when I say temperate boreal regions, think like Alaska, Canada, North America, like the Pacific Northwest, Northern California. Those would all be like temperate boreal regions, or at least that's how I'm defining them here, based off of the research that I'm referring to. Okay, and there's one other really interesting distinction to make here between tropics and temperate regions is that fires in the tropics burn at higher temperatures. It's not so much the fires at higher temperatures, but the higher temperatures just inherently. So, regions near the equator are going to be warmer. So higher temps near the equator result in hotter fires, and therefore more complete combustion. So what I mean by that is, in the tropics, our generalized chemical reaction for wildfire burning is mostly true. The chemist in me wants to balance this, so I'm just going to do it. So this reaction is mostly true. So the warmer temperatures allow for more complete combustion, so more just CO2, which, remember, CO2 is not considered organic carbon. It's considered CO2. I mean, it's not really relevant in particulate matter discussions and atmospheric chemical processes from wildfire emissions. So the more complete combustion from these hotter fires results ultimately in less organic carbon in fires that burn near the equator. So the plant matter, or rather the higher temperatures, more complete burning, less organic carbon, because most of it gets converted into CO2 completely. Okay? And inversely, the lower temperatures in the in the boreal or temperate regions result in more incomplete burning and more organic carbon as a result. Okay, so we're sort of setting the stage here for talking about how ozone production is going to be different depending on geography. So just to reiterate, the tropics, more NO, lower organic carbon. The temperate regions, less NOx, more organic carbon. Okay? And you might think, okay, but they're still both present, so won't they still both form ozone? Yes, but the time scales end up being very different for ozone formation, because one type of organic carbon that's very important is what is called peroxyacetyl radicals. So again, more radicals, more molecules with just one unpaired electron available, which makes them very reactive. But what these peroxyacetyl radicals do, so let's give a chemical formula for this. This would be C2, thinking of the structure, C2H3, I think, yeah, and then O3. So peroxyacetyl radicals have this chemical formula, C2H3O3. So remember, peroxy, extra oxygen, so this thing has kind of a lot of oxygens going on. But anyway, what these can do, these can react with NOx. So these can react with I guess technically NO2 specifically, and they can form what is called peroxyacetyl nitrates, or C2H, oops, that should be a 3, H3O3, or rather, we're adding, so we added these 2 oxygens to it, so it's O5 now, NO5. So these peroxyacetyl nitrates, often abbreviated as PAN, these PANs deactivate the NOx. So these deactivate NOx, which ultimately ties it up, resulting in low ozone formation, at least initially, okay? So just to reiterate, lower temperatures in temperate regions, so think fires in Canada or Alaska or the Pacific Northwest, those wildfires have more organic carbon and as a result produce more of these peroxyacetyl radicals, which can react with NOx and prevent it from forming ozone. Because remember, the way ozone forms in smog is because NO2 absorbs UVA to form a free oxygen, which ultimately forms ozone. So these peroxyacetyl radicals remove NO2 from this equation, ultimately not allowing ozone to form initially. Okay, so there's a caveat here. And so what happens in the case of these temperate regions, let's go to a new slide. So for these temperate regions, what ends up happening is that, hello, I want to draw. The PANs slowly thermally decompose. So just because of existing in heat, they very, very slowly break apart to reform NOx. And form ozone much later than when the fire occurred. Much later than when, let's say, the smoke was generated. So it's not an instantaneous process in the case of these temperate wildfires or wildfires in temperate regions, because the lower temperatures result in more incomplete burning, more organic carbon. This organic carbon includes peroxyacetyl radicals, which tie up the NOx, don't let it make, they don't allow it to make ozone. Slowly but surely, these PANs degrade, decompose, freeing up the NOx again, and allow it to then form ozone, in some cases like 200 days after the fire event, okay? So this can be particularly dangerous and harmful because the location of the wildfire doesn't matter as much for ozone production, because if there is significant wind, the smoke plume can be carried thousands upon thousands of miles in the matter of days, which can then significantly harm the air quality essentially globally. So this is a really, really big problem with temperate wildfires specifically, okay? So we'll talk a little bit more about this with a specific example from an Alaskan wildfire, but for now, let's just round out or finish up our tropics. So in the tropics, ozone forms more quickly. So as a result, the ozone formation the impacts of that is more of a local impact. So let's say more localized ozone formation, meaning that the region surrounding the wildfire is where most of the ozone is going to form and where the air quality gets really, really bad. Okay? And it is specifically in the temperate regions. So in the temperate regions, ozone forms much later and can impact a much wider area depending on how wind disperses the smoke plume. Okay? So let's look at a quick example of that. We're almost done, I promise, of an Alaskan wildfire here. So this is like a study where researchers did like a time distance dependence of ozone formation from an Alaskan wildfire in 2004. So a little bit dated, but still, I mean, wind is wind. It's not like it's going to be drastically different. I mean, it will change depending on weather events and stuff, but I guess what I'm trying to say is don't focus on this being an older study. It's interesting results nonetheless, okay? So what these researchers did is they actually used one of the coolest things, one of the coolest like instruments ever, I think, is the NASA DC-8. It's sort of like a mobile flight laboratory. So inside of this plane, there's like instruments and measurement tools that allows atmospheric scientists to essentially fly around and collect measurements on the atmosphere composition, which I think is really interesting. And this is sort of tracking the flights that were taken, ultimately tracking the smoke plume as it migrated to their final measuring point, which was in what was it called? It was a German word. It's like Frau. Oh no, it was Jungfraujoch is the name of the town. It was a town in Germany, I'm gonna guess. It looks almost more like Netherlands. Geography's hard. Um, who cares? They eventually went to a town in Europe. Let's just say that. And it was called Jungfraujoch. And what these researchers did essentially is they just measured ozone content in the plume as it was traveling towards Europe, and they measured the relative ratios of peroxyacetyl nitrates to ozone to like measure how quickly or slowly they formed ozone or like converted back into NOx to form ozone. And they found some really interesting results. So the first being is that the amount of ozone formed depended very heavily on water content in the atmosphere that the smoke plume was traveling through. And really, the big reason for this is that water is a precursor to that hydroxyl radical that we talked about before. And remember, hydroxyl radical was sort of the thing that started the whole formation of smog. It reacts with organic carbon to form peroxy radicals, which react with NOx to form NO2, ultimately forming ozone. So the OH is going to be formed from water, so it makes sense that the water content in the air would be relevant. And it also depended heavily on available light. So, and available light, which makes sense again, because to form ozone, you need UVA light to split NO2 to form that free oxygen atom, which will react with a molecule of O2 to form ozone. And then what they found, and this part really blew my mind, is that it was 206 days of travel, essentially. So here, let me rephrase this so it makes a little bit more sense. So they followed this smoke plume. So they tracked smoke plume for, I think it was for a total of like 220 days, something like that. But what they found is that there's a 5-day period from like 206 days to 211 days, it was something like that. Um, so they found that from 206 days until it reached Europe, um, and ozone levels in this town, Jungfraujoch, that's an A, increased by 20 parts per billion. So there's that unit again, but just remember, at least in the case of LA, which to be fair is a bigger city, they reside at about, kind of teetering on the edge of what is the maximum permissible value, like around 50. So 50 parts per billion. So what was observed in this town in Europe is that ozone levels increased by 20 parts per billion over a 5-day period. Which is pretty substantial considering that this wildfire occurred, halfway across the world essentially, and this smoke plume was able to travel all the way to Europe, raising ozone levels by 20 parts per billion, which in some cases, like in larger cities, that is a very substantial amount that will cause very, very poor air quality. And it really just demonstrates the global effect wildfires can have in terms of air quality, which is really both alarming and interesting, I would say. And in fact, New York wasn't the only city impacted by the wildfires in Canada. I think I saw an article in Scientific American that was focused on Denver, Colorado. So if we go back to that Canada fire map here, so there was a lot of fires, in Western Canada as well, and the ozone levels in Denver rose by, I believe the number was like 40 parts per billion. I tracked down the article, and they actually had a yearly average of 40 parts per billion, so similar to Los Angeles, and some areas in Denver rose up to 81 parts per billion, which is above the maximum permissible levels, and at the point where you're starting to have some possibilities of harmful health effects that result from breathing in this poor air. So yeah, so hopefully you have like a little bit more of an appreciation for the type of effects wildfires can have in the troposphere. This is certainly not an all-encompassing lecture. Like we didn't talk about like acid rain, for instance, which is another thing that could happen. But yeah, so hopefully this was sort of interesting here. And what we're going to be looking forward to next is soil and water chemistry in our next lecture. So we've been focused on the atmosphere, on the air for these last 2 lectures. What about, on the ground or in the ground, underground? What happens there? So some really interesting stuff there. And then we'll also talk a little bit more about the impact the type of vegetation has on the wildfire byproducts, and the impacts that can vary as a result. Okay, so hopefully this was an interesting lecture. Hopefully it wasn't too much. I realize with some of this photochemical smog reactions, it can be a little overwhelming. If you feel like you're just very lost with all of this, please let me know. I'm happy to provide you with other resources, other ways of viewing the information, or we could talk over Zoom to help clarify any confusion you might have. But yeah, I think that's all I had for today. So thanks for tuning in, and I will see you in the next lecture video.